Okay, so far we've only worked on symmetrical alkene addition reactions, and now we're going to look at this unsymmetrical alkene that has a CH3 on one side of the alkene. So things at first aren't going to look any different. We have our pi bond, our electrons. Those are going to be attracted to the partial positive on that hydrogen. So we're going to show an arrows like that to indicate that the hydrogen is adding to that, the pi bond is adding to that hydrogen, and the HCl bond is breaking. And that now brings up a new question, right? If we add the hydrogen to this side, that would make us have a CH3 and H, and the positive charge would be on that side. Or we could add the hydrogen to this side, that would make the positive charge right there. Or maybe the third option would be that both happen. So if we were in class, we'd do this as a clicker right now, A, B, or C. Which one would you expect to happen in this reaction? Okay, so taking a minute to think about it, you've added your answer in, and in the previous cases, the answer was both, right? We had the hydrogen add to either side, and either side was kind of identical when it was an unsymmetrical alkene, but it turns out that that's not going to be the case here. We're actually going to form the molecule that's more stable. So if you selected both, you're out, but not really. I mean, you're going to revote now. What would you expect to be the intermediate that is forming fastest, the most stable thing, the lowest activation energy, A or B? Okay, you revoted, that's good. And your votes said that A is out. So why did we form B preferentially? Well, this is a secondary carbocation, and this is a tertiary carbocation. This could say that the carbocation will form, the C plus will form on the more blank carbon. What should we write there? It's a more substituted carbon. We can write that. But why did the carbocation go there? Well, what's the most stable type of carbocation that we've learned about so far? It would be tertiary, right? This is a tertiary carbocation. This is a secondary carbocation. So the energy of the tertiary is lower than the secondary. So we're going to form the species that is the most stable. So that's the first step in this reaction. We form that preferentially, and the Cl minus adds there. So is it going to add to the top, the bottom, both? The answer is always both with these addition of a nucleophile to an empty p orbital. It can add to either the top or the bottom, and that would mean that maybe we're going to draw something like that and something like this, right? Potentially. And it's true, both of these things, like the Cl can add to the top or the bottom, but it turns out that when we draw both of them in, we're being a little bit extra, and we don't want to spend extra effort, right? Why do we not need both of these molecules that we've drawn up here? Other times when we've drawn up multiple molecules, it's because there are multiple different molecules that form. Are these molecules different? No, they're the same. This is not a stereocenter. We wouldn't want to imply that that's a stereocenter and tell people, look, we're making multiple things, when they're actually the same thing. So the only product that we would need to draw in here would be the chlorine and the methyl group with no stereochemistry implicated, because this is in fact not a stereocenter, and this is an achiral molecule. So that's what we would need there. All right, so this is a great time for you. We've learned a ton about these hydrohalogenations. Go ahead and just predict the products, guys. Just predict them out. I'd probably run through the mechanism. So go ahead and do that. Pause now, do that, come back. Okay, cool. This is an unsymmetrical alkene. The stuff on this side is not the same as that side. But the initial carbocations are going to look really similar, right? If we add the hydrogen to this side, we're going to have that carbocation. And if we add the hydrogen to this side, we're going to have that carbocation, right? So we have secondary carbocation versus secondary carbocation. So both of these things are going to form. I'll bet a lot of you maybe predicted that the products would have the chlorine in this location, and it theoretically could add to both sides. So we'll do the squiggle. You've seen the squiggle before. So yeah, that squiggle, just in case you don't remember, the squiggle means that it's a mixture of the wedge and the dash. So theoretically, this molecule here would create that there. And this carbocation here, the Cl minus would add there. So yeah, we'll just add Cl minus, adds there to make that. And if it added to the other spot, it would make that, right? So I'll bet a lot of you, when you were predicting the products, probably came up with these sets of molecules. So 2 molecules here, 2 molecules here. But it turns out that this is a product, but this one is not a major product. Why might that be? So maybe go back to where we are right here, this forms, but what might happen next in this reaction? So the chlorine could theoretically add there, but this is a secondary carbocation, both of them are. Is there any more stable carbocation than a secondary? Yeah, there's tertiary carbocations, right? And this one can't get to a tertiary by a single hydride shift, whereas this one here, this CH, that bond, the electrons in that bond can move from here to here. So 1,2 hydride shift to make the carbocation tertiary. So we went from a secondary carbocation to a tertiary carbocation. So this is a more stable carbocation than that one. We still are going to form these two things because initially the molecule doesn't know. It can't see the future. It can't say, if I add the hydrogen here, then a hydride shift is going to occur, then we're going to get our tertiary carbocation. It doesn't know that yet. But when it roughly 50% of the time makes that carbocation, this intramolecular hydride shift is going to happen at a faster rate than the chlorine adding to that molecule, because intramolecular reactions are faster than intermolecular reactions. At this point, we have our more stable tertiary carbocation. Cl minus is going to bump into that, and that will produce our other product, which is achiral. So I will not draw wedges or dashes or squigglies there. So this mixture of 3 molecules is going to be our product mixture. So again, we really need to be working hard on these mechanisms to ensure that we are able to predict these products. Because if you just look at this alkene and you say, oh, hydrohalogenation, add a hydrogen, add a chlorine, you're going to miss out on the idea of this hydride shift. And also you're going to miss out on the, is it syn, anti, whatnot, exactly. So, work hard on these mechanisms.